Hello everyone, can you hear me? Okay, as you can see today I have changed the appearance of everywhere. I have covered all the sources of light and I hope you like this new appearance better. Okay, shall we start talking about the problems today? How was the contest for voice is low, let me see for a second. Okay, now their voice should be high, right? Voice is high now. Contest was good. Awesome. Okay, yeah, today we will talk about the solutions of problems A to E. Unfortunately, I didn't have enough time to accept E at the end, but we're going to discuss a solution. I see. So we're going to solve all of them today. Let's see how it's going to go. Let me start with problem A. Well, problem A states that assume you have a multiset of numbers. You have a multiset S. The multiset contains only one positive integer n. Let me check everything is okay. Yeah, the multiset initially has only integer n, and each time you can choose a number, remove it from your multiset and replace it with at most k positive integers. Okay, you can insert no more than k positive integers into S instead. At the end, you want to have n ones. What is the minimum number of operations in order to have that? Okay, so what I say for this is this. Well, initially, we have a multiset S. Initially, as it is said, initially this multiset only consists of n ones, only one n, and we want to get n ones. And we also know that each time we know that the number of integers, the size of our multiset, can be only increased by the size of multisets, can be at most increased by k minus 1. Because each time we first remove one element and then add at most k elements, right? So we first remove one element and then we add at most k elements. So the size can be added, the size of the sets will be added by at most k minus 1 each time. And I know that initially my size is 1. And at the end, my size should become n. Because initially I have only one number, at the end I should have n numbers, n different numbers. And n numbers which are all 1. And each time my size can be increased by k minus 1. So my size should be increased by n minus 1, I know that each time I can increase it by k minus 1. So I can say that there's a lower bound for the number of operations, and that is n minus 1 over k minus 1, the sale of this value. Because each time I can increase it by k minus 1, I need at least the sale of n minus 1 over k minus 1 in order to make the size equal to n. So my answer cannot be better than this. My answer is at least this much. Do you all agree with this? And then I can show that the answer is at least this much as well. If you agree so far, I would appreciate it if you use this emoji so that we can make sure that everyone are on board. If you were not okay with any part, just tell me to repeat that. Yeah, I will repeat this part. I'm saying that each time I'm removing one element and then add at most k elements. Therefore, my size can be only increased by k minus 1 each time. At most increased by k minus 1. Therefore, I know that when initially my size is 1 and at the end my size becomes n, I know that the number of operations is at least sale of n minus 1 over k minus 1, because each time the size will be increased by this much and it should be increased by n minus 1 in total. Therefore, I need at least these many operations. So this is a lower bound for my answer, and I can show that I can do it with these many operations as well, because each time I can just change my number. Initially my number is n. I can change it to k minus 1 once, k minus 1 once, and 1 n minus k minus 1. So each time I have several ones and I have an integer greater than 1, x. Each time I take that integer greater than 1 and I turn it into k minus 1 once and one integer x minus k plus 1. Each time my maximum will be decreased by k minus 1. And I'm generating k minus 1 new ones each time. So I also have an algorithm to do it in sale of n minus 1 over k minus 1. Therefore, the answer is exactly this much. I know that the answer is at least this much, and I also know that there is a way to do that in these many steps. So the answer is this much. Is it clear? Shall we move on to the next one? If you are okay with that, please use this emoji or say that in the chats so that we can move on to the next one. If it is clear, we can move on to problem B. Okay. Lots of people are doing cheating, really? That's bad. If I don't know what's can happen from CF side, but I hope that will be fixed soon. Okay, if there are no questions, there are a lot of cheaters, really. That's really bad if that's happening. Okay, so let's move on to problem B. Problem B, make majority. It says that you are given a sequence a1, a2 to an, and each element is either 0 or 1. You can apply several possibly 0 operations to the sequence. In each operation, you select two integers l and r, and replace a of l to r with a single element x, where x is the majority of al to ar. And the majority is defined like this: if the number of zeros is greater than or equal to the number of ones, the majority is 0. Otherwise, the majority is 1, if the number of ones are strictly greater than the number of zeros. At the end, you have to say that, is it possible to make the array into one element of 1? At the end, you just want 1 in your final array. You have to say if that is possible. So what we can say in here is each time why we do an operation. I mean, if C0, if the number of 0, if we choose a sub array, if for example we have this sub array in our array and we choose it, there are two ways: either it will be turned into 0 or it will be turned into 1. Why should we turn a sub array into 0? Why should we pick a sub array and turn it into 0? Well, the only reason behind that, the only logic behind that, is to choose a sub array such that it has a lot of zeros, and by doing this, by turning turning it into 0, we're going to have only 1 0 instead of so many zeros. So for example, assume that we have 5 consecutive zeros. Well, the point is, when you have 5 consecutive zeros, you can choose these segments and turn it into just 1 0. And this way the number of zeros will be reduced by a lot. So this operation is going to be useful for us in order to reduce the number of zeros in our array. So initially, the first thing that I can say is that in each block that contains only zeros, when I see several consecutive zeros, I can have an operation on them and turn them into only 1 0. This operation will not have any harm. So if previously there was a solution to get a single 1 at the end, after doing these operations, still there is a way, because you did nothing but just removing some zeros, and you know that having less zeros in none of your operations, having less zeros will not have a bad effect. The only effect it can have is that instead of a 0, you get a 1 in some operation, which is at least as good as getting a 0. So I'm saying that when you see several consecutive zeros, there's no issue in choosing this interval and changing it to a single 0 instead of several zeros. This is always possible, and there's no reason that we do not do this. So what we can do, we can greedily each time for several consecutive zeros, we can just choose them and turn them into 1 0. This way, at the end, we are going to have several blocks of zeros and ones, and we know that each time we have 1 0, then several ones, and then again only 1 0, and then several ones, again only 1 0, several ones, because in each block there cannot be more than 1 0 this way. Because if it is, then we are sure that we can choose that subsegment and turn it into 1 0. So this way we are going to be sure that each of these have only 1 0, and we can say that in here now, if the number of ones is greater than the number of zeros, the answer is definitely yes, because we can choose the whole array now and we are gonna have a 1 and we reach our goal. But if the number of zeros is greater than or equal to 1s, the point is that we can never do something such that the number of 1s become more than the number of zeros. The number of zeros always will be greater than or equal to the number of 1s. Because each time when you choose a segment, if it has more zeros than 1s, if it has more zeros, then we know that the number of zeros cannot be more than 1. It cannot differ more than 1 from the number of 1s. Because in the best case scenario, I mean the only case, if we have more zeros is if we have exactly 1 0, then exactly 1 1, then exactly 1 0, exactly 1 1. This is the only case that in an interval we can have more zeros. And we are turning it into a single 0. So the difference between 1 and zeros will not change this way. So if we're turning an interval into 0, the number of the difference of zeros and ones cannot become better. That is not possible. If they are the same, they will become 0, and now we have one more 0. I mean the difference, the number of zeros, I show it with C of 0. C of 0 minus C of 1 will be decreased this way if they are equal number of 0 and 1s. If there are more zeros, it remains same. It remains the same. C0 minus C1 remains the same. It remains the same. If they are equal, C0 minus C1 will be increased by 1. I mean now we have the difference between the number of zeros and ones will be increased by 1. And if we are turning an interval into 1, again we know that the number of ones is more than the number of zeros here. So it is at least 1 more than the number of zeros. So we have more ones, and there are some difference between the number of ones and zeros in here, and what we get at the end is only a single 1. So again C0 minus C1 cannot get better by doing this. So I'm saying that when you do this operation, each block you change each block of zeros to a single zero, then afterwards you can never do any operation that can make the number of C0 minus C1 is smaller than what it is right now. So if right now C0 minus C1 is greater than or equal to 0, or in other words, the number of zeros is at least as many as the number of ones, it always remains like this. It always remains like this. There's no way that you can have more ones than zeros in future. And if the number of ones is already more than the number of zeros, well, then in one operation you can have what you want. And the answer is definitely yes. So in here, as I said, in here there are two cases. If the number of ones is greater than the number of zeros, let's show it with C0 and C1, then the answer is yes. Otherwise, if the number of zeros is greater than the number or equal to the number of ones, the answer is definitely no, because it always remains like this. There's no way that we can change it. So the point is that the solution for this problem is that for each block of 0 and 1s, for each block of zeros, we just turn them into a single zero, and then at the end we see if we have more zeros or we have more ones. If we have more ones, the answer is yes. If the number of zeros is at least as many as the number of ones, the answer is gonna be no. Is it clear? If it is clear, now I'm gonna show you my code. If you need any more explanation, tell me. Otherwise, I'll move on to my code. So here you can see my code. I just seen S and the size of it n, and I have a for. Each time I say that, you know, C0 and C1 is the final values that I will have for the number of zeros and the number of ones. Each time I say that if S of I was equal to 1, C1 plus plus, else I just have car. Car just keeps the current number of just keeps the current number of zeros in the last block, the current number of zeros. And when I reach the end of this string, my for goes up to n itself. When I was equal to n, it means that we are at the end of this string. Or S of I was equal to 1, which is we got to a 1, we can say that if car was non-zero, it means that we've had a block of zeros. Then C0 plus plus, and then car equals 0. We could also say that if S of I minus 1 was 0, I mean if I is equal to n, we are at the end of this string, or S of I is equal to 1, and S of I minus 1 was 0. It means that we reached the end of a block of zeros. So in here C0, I want C0 to be the number of blocks of zeros, and C1 is gonna be the number of ones. This is gonna be the number of ones. And at the end I will compare these two values. If C1 was greater than C0, the answer is yes, otherwise the answer is gonna be no. Does it make sense? Is it clear? If you're okay with that, please again write that on chat or use this emoji. Otherwise, tell me to explain it again. Okay. So let's move on to the next problem then. Problem C. Problem C, increasing sequence with fixed OR. This problem says that you are given a positive integer n, find the longest sequence of positive integers a equal to a1 to ak that satisfies the following conditions, and print the sequence. ai is less than or equal to n for all I from 1 to k, and ai is strictly increasing, that is a sub I is greater than a sub I minus 1, and ai or ai minus 1 is equal to n for all I from 2 to k, where or denotes the bitwise OR operation. So this problem is just saying that you are going to have you have a number n and you want to find the longest possible sequence a1 a2 to ak, such that first it is in increasing order, so a1 is less than a2 less than 2ak, and second, for each two elements, for each two consecutive elements, ai or a of I plus 1, each two consecutive elements, the OR is n, and ai's themselves are at most n2. So you want to find the longest possible sequence with the three conditions. Okay. So what can we say about this? The main thing that we can say in here is that, first of all, I show that if the number of bits, assume that, for example, let's consider a case like this third case here, for this fourth case here, 23. Consider this number 23. We have 23 in here. Let's write it in base 2 and see how is this in base 2. In base 2, 23 is gonna be a 1, then it's gonna be 11, then it's gonna be 5, then 2. So it's gonna be this number in base 2. So this is 23. I want to show that 23, when it has 4 bits which are 1, I want to show that the first thing that I want to show, if your number n has x bits which are 1, the answer is definitely x plus 1. Okay, so I'm just saying that the answer is, if you have x bits which are 1, the answer is definitely x plus 1. So how do I say that? For example, for 23 the answer is definitely 5 because it has 4 bits which are 1. How do I say that? I'm saying that because, and there's only one corner case, and that corner case is that if your number is of form 2 to the power of k, if the form of your number is 2 to the power of k, or in other words, it has only 1 bit, then your answer is 1, not 2. Your answer is not 1 plus 1, which is 2. Then the answer is 1 itself. So if you have only 1 bit, the answer is 1. Otherwise, if you have x bits, your answer is x plus 1. If you have only 1 bit, the answer is 1. If you have 2 bits which are 1, the answer is 3. If you have 3 bits which are 1, the answer is 4, and so on. Well, first, I want to say why if we have only 1 bit, then the answer is 1. Because the point is that, assume that we have a sequence of length greater than 1. For example, assume that we have 2 integers, a1 and a2. Well, a1 should have that bit. a1 should have that bit number k. So a1 should be equal to 2 to the power of k. On the other hand, a sub 2 cannot be greater than 2 to the power of k as well, because each number should be at most n. So it cannot be greater than 2 to the power of k. So the array cannot be increasing. This is a contradiction. This contradiction shows that if we have only 1 bit which is 1, the answer is 1. Is it clear so far? The elements are positive and they are in a strictly increasing order. So yes, they should be strictly greater than the previous number. Otherwise, we could have infinite n's. All the numbers should be n and they would be correct. Is it clear? Yeah, I will tell you that why for this case it is x plus 1. But for now, I'm just proving the first case. First, I'm saying that if the number of bits, if x is equal to 1, or in other words, we have only 1 bit that is 1, then the answer is 1. The answer is x itself. Is that clear? So all I'm saying is if our number n is of form 2 to the power of k, if it has only 1 bits, then if it has only 1 bit, we can say that our answer is going to be at small, our answer is going to be 1. Why? Because assume that we have 2 integers. Assume that the length of the interval is greater than, we have a1 and a2. Consider the first 2 elements. If the length is greater than 1, consider the first 2 elements. Well, I'm saying that a1 should be equal to n, because it cannot have any bits other than the bits in n. I mean, n in base 2 is something like this: 1 and then several zeros, 1 and then k zeros. So all I can say is that in here it's gonna have 1 and k zeros. I can say that a1 cannot be greater than n, because that's one of the conditions. Also, it cannot have any of these bits, because if it has any of these bits, then a1 or a2 will not be n, because n doesn't have these bits. So if a1 has any of these bits, then the answer is definitely no. It is not possible. Okay, so I'm just saying that this way a1 should be n and a2 also should be n, because a2 should be greater than n, but it cannot be greater than n. So on one side, because array should be increasing, a2 should be greater than n. But on another side, because all the values should be greater than, less than or equal to n, it cannot be greater than n. So there's no way. So if n is equal to 2 to the power of k, a1 should be equal to n when we have some a2 as well. So a2 cannot exist because your numbers cannot be greater than n. So the answer is gonna be n this way. So if you're okay with that, please again either say it in chat or use this emoji. Okay, after this, now we know that x is at least 2. So we have at least 2 bits such that I will show you my code. Let me first explain it and then I will show you my code. Assume that we have at least 2 bits which are 1. Then I can say that in this scenario, I say that my answer is gonna be at most capable x plus 1. First, I show that the answer is at most x plus 1, and then I'll show you that x plus 1 is indeed possible as well. So first I show that the answer cannot be better than x plus 1, and then I show you that the answer is gonna be x plus 1 itself. I show you that our our a sub I, so our numbers are a1, a2 to ak. I show you that in ai, the most significant bits of n, among the most significant bits of n has some bits on and some bits off. Among the most significant bits of n, in the first I minus 1 bits, the first I minus bits of them should be 1. What do I mean? Let's consider the example that I said, 23. We had 23 and 23 was equal to 16 plus 7 plus 4 plus 2 plus 1. I'm just saying that first I have these numbers a1, a2, a3, a4, a5 and so on. Assume that the answer is greater than 5, so we have a6 and so on. So consider the first 5 elements for now. I'm just saying that a1, in a1 the most significant bit should be on. Definitely in a2 the most significant bit should be on. So I'm saying that in a2, in the second element of the sequence, the most significant bit should be on. So we know that each one of them have 5 bits. For example, we are showing everything with 5 bits. I'm saying that in A2 this bit should be 1. Why do I say that? Because there are 2 cases. Either in A1 it is 1. If in A1 it is 1, then because our array is increasing, in A2 it should be 1 as well. Because we don't have any additional bits, our numbers cannot be greater than n. So if in A1 this bit is 1, in A2 this bit should be 1 as well. Okay, so the first case is that if in A1 this bit is 1, in A2 this bit should be 1 as well. Second, I say that if in the first bit this bit is 0, if in A1 this bit is 0, because A1 or A2 should be equal to n, then in A2 this bit should be 1. Right? So I'm saying that in A2 the most significant bit of n should be on. Is it clear? If you're okay with that, please again use this emojis or write that in chat. So I'm saying, and if it is not clear, just tell me to explain it again. So I'm just saying that for now, I'm just saying that in A2 the most significant bits of n is 1. So we are sure about that. Now consider A3. In A3, I want to say that the first 2 most significant of bits of n should be on. So the most 2 significant bits of n are these 2. N is equal to this. The first 2 most significant bits of n are this one and this one. These 2 are the most significant bits. I'm saying that in A3 both of them should be 1. And this one should be 0 definitely, otherwise it's gonna be greater than n. Why I'm saying that these 2 should be 1 in A3? Because again, we have 2 cases. About A2, we know that A2 is 1 here. And we are sure that A2 should be 0 here as well, because otherwise it is greater than n. About the third bit, either it is 1. If it is 1, then again in A3 it is 1 as well, because our array should be in increasing order. And guys, whenever you felt that you're completely okay with that and you understood it, you can use this emoji. I mean, whenever you felt that you are completely okay, you can use that so that I know that you got it. So if in A2 this bit is 1, then in A3 this bit is 1 as well. And if in A2 this bit is 0, again the same logic. If it is 0, again the same logic. We know that A2 or A3 is n. So in A3 it should be 1. So either way, in A3 this number should be 1. This bit should be 1. Okay. And then consider A4. Again on A4, I say that the third most significant bit of n should be 1. Again, the same logic. The first bits are going to be exactly like this because it is increasing, but at the same time it cannot be greater than n. Again, about the next one, if in A3 it was 1, in A4 it should be 1 as well. If in A3 it was 0, then in A4 should be 1, so that their OR is equal to n. So this bit again in here should be 1. And about A5, the last on bit of n should be on in A5 as well. So A5 is like this. So the point is, a of x plus 1 is exactly equal to n. Because in a of x plus 1, we can say that we know that n has x bits. N has x on bits. And we know that in a of x plus 1, the first x on bits of n which are all there, all the on bits in n are going to be on. Therefore, in a of x plus 1, a sub x plus 1, all the bits which are on in n are going to be on. Therefore, we can say that a of x plus 1 has everything that n has, and it cannot be greater than n as well. So it's going to be exactly n. So we cannot have some a of x plus 2. We cannot have some a of a sub x plus 2. That's not possible. A of x plus 1 is always a of x plus 1 is always going to be the last, is always going to be n, so it's going to be the last one. So we prove that the answer is at most x plus 1. Now we have to show that x plus 1 itself is possible. Is everything clear so far? If so far you have any questions, ask me. So if you don't have any questions, please again use these emojis so that we move on to the next question. Okay. So everything's clear so far? Good. Yeah, I will show you the code. Let me finish the explanation and then I will show you the code. So let's continue. So what is my solution to show that x plus 1 is always possible? In order to show that x plus 1 is always possible, I just say that in your number, just do this. Your a of x, a of I is like this. First of all, for a of I, you know that the first I minus 1 significant bits of n are going to be 1 in this one. So the first I minus 1 significant bits are on in a sub I. And then for the next on bits of x, I alternatively put 0 and 1s there. So for the first one of them I put 0, for the second one I put 1, for the third one I put 0, and so on. So for the next bits which are 1 in n, I alternatively put 0 and 1. This way you can easily see that a of I or a of I plus 1, a sub I or a sub I plus 1 is always equal to n. Because we know that the next time this bit becomes 1 as well, and these ones will alternatively turn into 0 and 1s. So you see that they will toggle. If they were 1, now they will become 0. If they were 0, now they will become 1. So the OR of these two, OR of a sub I and a sub I plus 1 is always equal to n this way. And therefore this is going to be our this is going to be a valid sequence. And this way you can easily see that we can have x plus 1 elements. We can have a1, a2 to a of x plus 1. A sub I is, like I said, a sub I is going to be the first such that the first I minus 1 on bits of n is going to be 1 in that one, and the next bits will alternatively be 0 and 1. The first one is 0, the next one 1, then 0, then 1. It starts from 0 always. Okay, so let me show you an example on 23. Let's see how do we make that. 23, as we said, is 1, 0, 1, 1, 1 in base 2. So my a of 0, a sub 0 will be this. My a sub 0 is going to be, do not forget that these are the on bits that we have. None of them are in that prefix that they are all 1. So they will alternatively be 0 and 1. So our a sub 0 is this, 0, 0, 1, 0, 1. In base 2, which is going to be equal to 5, right? Then a sub 1 is going to be In a sub 1, the first bit is now 1, is now fixed to be 1. And then the next ones, this one is always 0, because in n it is 0 as well. And then these three ones will alternatively be 0 and 1. So for this one we have 16 plus 2. The a of 1 is 18. Then for a of 2, we have these 2 bits 1, because we know that in each of them, I started my indexing from a sub 0. Maybe I should start my indexing from a sub I. Maybe it is better if it is 1 base indexing, because in my definitions it was one base indexing. So for a sub 3, the first 2 on bits are 1. So it's gonna be 1, 0, 1. And then these two will alternatively be 0 and 1. So this number is going to be 16 plus 4 plus 1. So it's going to be 21. Then a sub 4, for this the first 3 on digits are 1. So it's going to be 1, 0, 1, 1. And then the next digit is alternatively 0 and 1. So it starts from 0. So this one is 0. This is going to be 22. And a sub 5 is going to be all these on digits. So it's going to be 23 itself. 1, 0, 1, 1, 1, which is 23. So basically, this way I'm writing all the numbers in a way that a sub I, in a sub I, the first I minus 1 on bits are on, and the rest of them will alternatively be 0 and 1. Is it clear? Yeah, so let's, yeah, sure, I will try to speed up if everybody are okay with that. So let me show you my code as well. In my code, you can see in here, what I do is just this. I see in n, first I say that if built-in pop counts of n is 1, then just see out 1n. It's going to be only one number, and we will see out n, and then we say that res is equal to built-in pop count of n plus 1. As I said, built-in pop count is just the number of on bits. I see out res, and then I have a for on res, and I just say that for each one of them, if n had that digits, we have a CNT that says that which what is the index of this significant bits, which significant bit it is. So we can see that how many bits have we seen already. If CNT was less than or equal to I, in here in code we have 0 based indexing. So a sub I has I, the first I bits, the first I significant bits are going to be on. So if CNT was less than or equal to I, val plus equal to 2 to the power of L. Otherwise, we have a car that alternates between 0 and 1. If car was 1, we say that val plus equal to 2 to the power of L. Otherwise, we do nothing, and each time car becomes 1 minus car. So each time car toggles. So this way, at the end, we know that what this value is, and we see out val, and we see out endl. And this way, we're gonna have the final answer. Is it clear? Is it completely clear? If you are okay with that, please again use the emojis or write that in the chats. Otherwise, tell me. And if the majority of you wants to move on to the next problem, I can move on to the next problem. I should do what most of you want, so that it has so that this stream is gonna be useful for most of you. And guys, you always have the option of watching this video again. The video will be saved, and if any part was not unclear after the stream, you can watch that, or even during the stream you can watch that. You can just, maybe let me show you on the screen. You know, as you can see in here, this is my screen. You can see that you can choose where you want to watch. You can watch that part again if you want. So I'm just telling you that you have access to all these parts while we're doing this stream, and if you need, you can watch any parts again. So okay, let's move on to the next one, problem D. problem D says that we have several monsters, and these monsters are on a tree with n vertices. And we know that on vertex number I, we have a monster with attack points of a sub I. And we want to battle with these monsters for infinite number of rounds, for a very huge number of rounds. And each time all living monsters attack you, your health will be decreased by, your health decreases by the sum of the attack points of all those living monsters. And then you can select some of the monsters and kill them. And after being killed, the monster will never be able to do any attacks in the future. And it just has some restriction. It just has a restriction that in each round you cannot kill two monsters that are adjacent in your tree, that are connected by an edge in the tree at the same time. And if you choose these monsters optimally, these monsters that you kill, what is the smallest health decrements you can have after all rounds? So basically what we have in here is we have a tree. On each node of this tree we have a monster. We have a monster on each of these, and each time you can choose several of them which are not adjacent with each other and just kill those. And you want to do that in a way that, and each time first all of the monsters which are alive attack you, and then you can kill some independent set of them. And you want to minimize the total harm that these attacks will have on you. Well, what I say is like this. First of all, I say that in the final answer, there is no reason that more than log of n steps matter. So the first idea that I had on this problem was this. The first thing that I can say about this problem is this, that we do not need to consider more than log of n steps. Do you agree with this? Can anyone say why? So if we can say this is gonna be so helpful for us. But yeah, so the general point is that the number of if I want to end this, in shortest number of operations, I can even end it in 2 steps. I can first time remove all the vertices at even heights, and then I remove all the elements at odd heights. So if I want, I can even do this. First remove all the elements at even heights, and then remove all the elements in odd heights. And this way, in only 2 steps, all the vertices will be removed. But it is not always the most optimal case, because it is possible that by doing this, maybe there are 2 adjacent vertices, one of them is at an odd height, one of them is at an even height. And it is optimal if you keep both of them, because they are not very harmful. These monsters are not very harmful, and you want to remove these vertices adjacent to them instead. So at the beginning you will remove these ones, and you will keep these 2 adjacent vertices. And the next time, for example, you remove this one, and then you remove this one at the 3rd step. But yeah, as you said, we can always say that each time the vertices that we remove are going to, we can say that the damage that we're gonna have each time will be divided by 2, so that it will take at most log of n steps till all the tree will be removed. Okay, so I'm just saying that it will take at most log of n steps for everything to be removed, and therefore I can have only some dp of I and v, which says that what is the minimum cost, the most optimal way, the minimum cost if we remove vertex I, and let me say that what is the minimum cost in the subtree of v, in the subtree of vertex v, subtree of v, if we remove vertex v at step I. Okay, I see that like some of you have understood the solution so far. So that is the main idea. dp of I and v is the minimum possible cost in the subtree of vertex v if vertex v is going to be removed at step I. Okay, so the point is that dp of I and v is gonna be dp of I and v is gonna be, initially I can set that equal to a of v times I. Why it is gonna be a of v times I initially? Because v itself is gonna be alive in I steps. Vertex v itself is gonna be alive in I steps. So initially dp of I and v is gonna be a of v times I. That is how much that vertex itself contributes to the final answer. And I should add the dp's of children for each child. If this is vertex v and it is removed at step number I, for each child like u, I should see that what is the minimum of all the dp's of j and u such that j is not equal to I and j are not equal. Okay, so why I want to do that? Because if I want to remove the subtree of vertex v, first the subtree of vertex u should be removed as well. And I know that the step that I will remove u should not be the same as the step that I'm gonna remove v. So the step that vertex u will be removed is not the same as the step that vertex v will be removed. So it should be minimum of dp of j and u for all the j's not equal to I. And this is how I can calculate all the dp's. And I will tell you how to calculate it in a good time complexity. I don't want to have a 4 on j as well. I want to just have a 4 on I and v. I don't want to have an additional 4 on j. I will tell you how we can calculate these without having an additional 4 on j. But the general idea is this. So far we can have a solution with a bad complexity. We can have O of n times log squared of n. We can have a 4 on v, I and j, and so for each edge we have log squared time complexity, because we fix what is I, what is j. When I will be removed, where v will be removed, where u will be removed, and they should just not be equal, and dp of j, I and v will be added by this dp of this minimum for each j, dp of j and u. So the only thing that we need to care about is that the step that u is removed is not the same as the step that v will that u will be removed is not the same as the step that v will be removed. So that's going to be all that we care about. So how to calculate that? In order to calculate it in a good time complexity, if we want to improve this solution to O of n log n instead of O of n log squared of n, what we can say is just this. We can change this solution to that for each child like you, let's just keep the best 2 dp's. Let's keep the best 2 dp's. So it is, for example, dp of some j1 and u and dp of some j2 and u. So we keep the best two dp's for every u. Now when we are on I and we want to update dp of v and I from dp of u and some j not equal to I, we have the best two dp's, and if I is equal to j1, you should consider the second best dp. If I is not equal to j1, you can consider the first best dp, right? So this way you can remove an additional log. This way you can just have a simple O of n log n. You initially, for each child like you will save that what is the best two dp's, and then when you want to update dp of v and I, you just see that if I is equal to the best dp of u, if it is, consider the second best for you. If it is not, consider the first best for you. And then you can easily, in O of 1, you can find the best j. And this way you can calculate dp of v and everything. At the end, your final answer is gonna be minimum for all i's from 1 to log, minimum of dp of I and roots. So this is going to be your final answer at the end. Is it clear why it is not n squared time complexity? Well, the reason is that I just have a 4 on all the edges, right? For each v and u, such that u is a child of v, I do this. I have a 4 on i's, and then I update dp of I and v from dp of something and u, something that is not equal to I. So for each edge, I'm updating this dp. The number of edges is n minus 1, so it's from O of n. And we have also 4 on I, which is log of n, and then we find the best j in O of 1. So in total, our time complexity is gonna be O of n log n. Is it clear now? Yeah, I can show you my code as well, if you want. Yeah. Yes, sure. So let me explain more on my code. So if you see my code here, I just said that first initially, as I said, there are going to be at most log steps. You can easily see that each time, you know, the damage of the vertices that you're going to have, the damage of the monsters that you're going to have will be halved. So each time you can say that at most log of n, you're going to have log of n steps. And in log of n steps, you're gonna know that you're gonna kill all the monsters. It doesn't take more than that. So you just need to know that in which step this monster is going to die. So dp of I and v says that I want to kill every monsters, or in other words, let me tell you like this. dp of I and v says that I'm just considering the monsters in the subtree of vertex v. I'm just considering the vertices in the subtree of vertex v. And I want to see that what is the minimum cost if vertex v itself will be dead at step I, at step number I. And because it is zero-based index, for example, a dp of 0 and v means that after the first time they attack me. So dp of I and v is initially I plus 1 times a of v, because 0 is the first possible step that you can kill them, and if they die at step 0, it means that they attacked us once. So dp of I and v is initially, if I only consider this vertex itself, dp of I and v should be set equal to I plus 1 times a of v. And then I'm gonna have a 4 on all the adjacent vertices of v. If u was equal to parents, I will continue. and then I will have DFS of u and v, and I keep the best DPs of u. Each time, for each DP of u, I say that mn2 is equal to minimum of mn2 and DP of I and u, and then I say that if mn2 was less than mn1, swap mn2 and mn1. This way I just keep it. mn1 is the best DP for j, for u, and mn2 is the second best DP for u. So I keep these two values, and then I have a for I from 0 to log, and I say that I set value as mn1 initially, but I say that if value was equal to DP of I and u, it means that if this minimum value was for the same step, was for the case that u was being dead in the same step, set value as mn2 instead. So I initially set val as mn1, but then I check if that was equal to DP of I itself and u, it means that u and v are going to die in the same step, that which it doesn't make sense, which should not happen. Then I consider the second best DP for j, and then I say that DP of I and v plus equal to val. And then at the end, after this DFS, I set ans equal to inf, and I have a for each time I say that ans is equal to minimum of ans and DP of I and 0. 0 is the root of my tree, so it's gonna be DP of I and 0. So this root will be dead in this step I, and everybody are going to get killed. And at the end I just see as ans, and then I clear the adjacency vector. Does it make sense? Let me read your comments. The number of steps is a constant 3. I don't know about that. Can we prove that it is at most 3? Let me see. Let me see if anybody has proved that. Let me see the editorial if they show that it is. No. Also the editorial is using the fact that the rounds is log of n. The number of rounds is log of n. And let me see that, how do they say this? Editorial is also out. Maybe it's good if we all say it together. The way they prove it is to say that let the mix of a set be the smallest positive integer that does not appear in it. Note that in an optimal arrangement, ba sub I is equal to mix of for each of its adjacent vertices. That is right. So in the proof that they provided is that each vertex will be removed in a step that is mix of all the adjacent vertices, because it's the first step that all other adjacent vertices are not getting removed. So it will be removed then, because there's no reason that you remove it later, because you can remove it now with no cost. Okay, and then consider a vertex with maximum b equal to u. Root the vertex at this vertex. The vertex is connected with x should take all b's from 1 to u minus 1. Okay. Cool. Yeah. So if you want, I can tell you the proof that they have for the case where the answer is going to be at the number of steps is at most log n. Well, the way they prove it is this. They say that, assume that, well, first of all, they are saying that for each vertex, like vertex v, it's always optimal. I mean, it doesn't make sense that at the end, for vertex V, the step that it's being removed is not mix of all the adjacent vertices of V. It doesn't make sense. That's a contradiction. Because if that happens, for example, this one will be removed. Let's use 1 based indexing. This one is removed in step 1. This one is removed in step 2. And this one is removed in step 4. And also this one is removed in step 1, for example. Then V definitely should be removed at step 3. V definitely will be removed at step 3. We can easily prove that by contradiction. Let's say that it is not like that. V is not removed at step 3. Then we can say that, for example, V is removed at step 5. Then we can say that we could instead remove it at step 3. And we had a better answer. This is a contradiction. This shows that this is not possible. Okay, this shows that this is not possible. So at the end, the first thing that we can see, the first observation is that at the end, the step that each vertex is removed is equal to max of all the adjacent vertices of it. Because it cannot be equal to all the adjacent vertices, to any of the adjacent vertices. And second, it can be the smallest element that is not equal to them. If you make it larger, that's a contradiction. That shows that this answer is not optimal. Okay, so first of all, it is max. So for each vertex, the step that it will remove is the max of all the adjacent vertices. And then second, after that, I can say for all the vertices that we have, assume that for the last vertex that will get removed is some vertex U. Some vertex U is the last vertex that is being removed. And it is removed as step number K. Okay, some vertex, let's call it vertex R. We set this vertex R as our root, that we set this vertex. Let's use V. V is a vertex that will be removed in the last step. So it has the maximum. The step that it will get removed is maximum. If there were several maximum, just pick one of them. The point is that for V should have an adjacent vertex, V should have a neighbor such that it will be removed at step 1. Also, it should have a neighbor that it will be removed at step 2. Also, it should have a neighbor that it will be removed in step 3. And also, it should have a neighbor that it will be removed at step K-1. Okay, so it should have all of this. It should have all of these. So now, if you define f of k as the minimum possible number of vertices, the minimum number of vertices such that it is possible that one vertex will be removed at step K. One vertex will be removed at step K. So that is f of k. What we can say is that f of k should be at least equal to sum of f1 to f of k minus 1. Okay, so we can say that f of k should be at least equal to sum of f1 to f of k minus 1 and also an additional one for v itself. So one vertex is v itself. There are at least f of 1 vertices in here, based on the definition, because we know that we should have at least f of 1 vertices, so that one vertex will be removed at step 1. We should have at least f of 2 vertices in here, and we should have at least f of k minus 1 vertices in here. So f of k is equal to at least 1 plus f of 1 plus f of 2 plus 2 f of k minus 1. So it is 1 plus sigma of I from 1 to k minus 1 f of I. And by induction, it is easy to prove that with these conditions, f of k is greater than or equal to 2 to the power of k. Why? Because if we use induction, we can simply say that if this is true for the previous values, then this is greater than or equal to 2 to the power of 1. This is greater than or equal to 2 to the power of 2. And this is greater than or equal to 2 to the power of k minus 1. And the sum of these values is exactly 2 to the power of k. So the whole thing is greater than or equal to 2 to the power of k. So f of k also is going to be greater than or equal to 2 to the power of k. Okay, so the point is that if one vertex will be removed at a step k, we need to have at least 2 to the power of k vertices. So therefore the number of steps is at most log n. And then using this proof, we know that the number of steps is at most log of n O of log of n, then it is at most floor of log of n plus 1 to be more precise. Then we can use dp of I and v, as I said, where I is up to log of n plus 1 and v is up to n. And we can solve the problem in O of n log n. Is it clear? Yeah, you're welcome. So this is gonna be the whole proof. It was an interesting proof. Yeah, now everything is very precise. So, shall we move on to the next problem? Problem E. Problem E, unfortunately, I used stack for solving it, but couldn't finish the code till the end of the contest. Let me see that what the editorial used. Let me see if they used the same approach. Cartesian tree. There's this is okay. Seems like they used another approach. They are using Cartesian tree. So maybe it's best if I tell you first about Cartesian tree. And guys, if you liked the video so far, I would appreciate it if you like the video or subscribe to the channel. I think that's gonna help me. But anyway, so let's talk about Cartesian tree because it seems like they've used Cartesian tree. So for problem E, but let me just make sure, let me find their solution completely, and then we talk about Cartesian tree as well. So they build a Cartesian tree, consider vertices. If we delete it, what would happen to the three vertices that are on the outside of X's subtree will not be affected. Vertices inside the subtree of X will merge. Yeah, because X is the smallest one of them, definitely. Yeah, they will merge. Actually, you can see that on the right chain of X's left child, oh, cool. Yeah, that is exactly what I wanted to do. But I didn't use the topology of Cartesian tree, but that was exactly what I was trying to do. This was my code. I used a stack and I was exactly doing something similar to merge sorting here. But yeah, it is for merging them, and the time complexity is of n. Cool. Okay, so let's talk about it. So let's talk about it. Problem E just says that for any array a1 to an of length n, we define f of a as the sum of the minimum elements over all subsegments. That is, f of a is equal to this value. And then you are given a permutation each time, and it is a permutation. Each time you erase some a sub I from A and concatenate the remaining parts, and you call that B, and you have to calculate f of B. So in the output, you should print n numbers. Each of them show if you have removed one specific element of your array, your permutation. So what do we say? The solution says that assume you have a Cartesian tree. Cartesian tree is something like this. For every vertex, you first consider the smallest number in your array as your root. So if you have a permutation, 1 is your root. So let's just write a random permutation. For example, we have 4, 9, 3, 1, 5, 2, 7, and what is left? 8 and 6. 8 and 6. So Cartesian tree is like this. First, it gets the minimum as your root, which is this one, and then solves the two sub-arrays independently, recursively, and then puts them as children of this vertex. So first puts 1 as the root of your tree, and then solves this part, this left part, recursively, for example. When you solve this part recursively, again, you have to put 3 as the root of your tree. You put 3 as the root of your tree, and then you solve this part recursively, then you should put 4 as the root of your tree, and then you should put 9 as the root. So this is the Cartesian tree, and everything to the left is in your left children, and so you have a left child and right child for each vertex. Everything to the left is for your left children, everything to the right are for right children. And the same holds in here. You have this 2, so 2 becomes your roots in here. The left part of root, you just have a single 5. In the right part of 2, you have the smallest number is 6, and then the smallest vertex in this interval is 7, and then we have 8 here. So this is gonna be your Cartesian tree, and it is defined like this. Each vertex is less than all the vertices in its subtree, and also everything to your left are the numbers which are really to the left of you, and everything in your right children are really the vertices in the right children of you. So these are the values that you're gonna have in your Cartesian tree. And now this problem, we say that if we remove some number x from our permutation, first of all the intervals, only the intervals containing numbers in x will get affected. In the subtree of x will be affected. So it means that by removing x, nothing will change other than the subtree of vertex x. Okay. So only subtree of vertex x will be removed, will be changed. And how do we merge them? I mean, we have two subtrees for x. We have two subtrees for x. And when x will be removed, it's like we are going to have some merge sort on them. I think it should be on the right chain of the left child and the left chain of the right child. Yes. So when you remove this vertex from your Cartesian tree, if you consider this right chain of this subtree and the left chain of this subtree, it says that they will get merged. How? It is somehow similar to merge sorts. Why? You know, we have, I mean, x initially, x has two children like y and z. When you remove x, the smaller one between y and z can become the parent of the other one. So if you consider this left chain of this right subtree and this right chain of this left subtree, each time you can see that it's like you have a pointer on these two. Each time you see that each of these two values is smaller than the other one. You have a pointer, you have two pointers, one on here and one in here. Each time you see that which one is smaller, for example, you see that y is smaller than z. Then you put y as the root, and then the left child of u is fixed. The left subtree of u is exactly the left subtree of that you had. And again, in your right subtree, you need to merge these two parts. Recursively, you need to merge these two parts. Again, you will compare this one with this one. This pointer goes forward. And you compare these two ones, again the minimum comes here. For example, if the next time z is the minimum one, if this is z and this is for example t, z comes here, then the right subtree of z is going to come here. In the left subtree of that, in here, again you're gonna merge these two chains. So it says that when you remove x, you can merge these two. You can merge this subtree like this. Okay. And now we want to see. Okay, now it says a very beautiful fact, I think. It is just saying that if you do this, the total time complexity is going to be O of n. Because each vertex will be considered only once. Yes, a very beautiful fact in here. A very beautiful fact. Let me write it here. Very beautiful observation is that in total, if you do this for all the vertices, it's going to be O of n. Why? Because if you see these vertices, you only do this for these vertices only once. Because each vertex is either the left child of its parent or is the right child of its parent. Every vertex is either the left child of its parent or the right child of its parent. Without loss of generality, assume that it is the right child of its parents. If it is the right child of its parent, we should go up as long as these vertices are the right child of their parents, and consider the first time that this vertex is now the left child. Now, so start from a vertex is either a left child or a right child. If it is a left child, so if its parent is to the right of itself, it is a left child of its parents. We should go forward, we should go upward, and when we go upward, we will keep going right. And the first time that we change our direction, that's gonna be the only time. Only for this vertex, these vertices will be considered. So the point is that all these vertices will be considered only once. And in total, merging this Cartesian tree is going to be O of n. Because when you have a 4 on all these vertices, each time these pointers go downward, the total number of times that these pointers move is going to be the size of this chain plus the size of this chain. And these vertices are going to be only in one chain in their lifetime. I mean, in the whole tree, they're going to be only in the chain of this one. Because it's like we start from these vertices, we go to the direction of their parents, and we consider the first time that they're not, the direction changes. So they will be considered only once, and the total order is going to be good. Does that make sense? Does it make sense so far? So far, being permutation didn't make any difference. Well, I mean, didn't make any difference other than that they are different. So I'm not sure if instead of permutation, we were just saying that if all the numbers are different, the answer would be any difference. I think that it was still solvable if it was not a permutation, but instead we could say that they were not necessarily a permutation, but they were different. I think that will still work. Okay, and now the point is that when we construct our Cartesian tree, this Cartesian tree should make it easy for us to calculate that, to find out the answer. Why? I'm just thinking that what is the easy way to calculate the sum when we have the Cartesian? So far we understood that finding the Cartesian tree is easy. I mean, in total, this brute force takes O of n. But the point is that when you have this Cartesian tree, when you have a number x, for example, you know that the parent of x is the first vertex in one of the directions that is smaller than x. So yes, it is easy. Because, again, consider some vertex x. If you have this Cartesian tree, again, assume that this is the left child of its parents. Then you know that the first vertex to the right of it, that is less than it is its parent, like y. Let's name it y. The first vertex to the right of it that has a value less than it is its parent vertex y, and the first vertex to the left of it that has a value less than it is the first time that we go to a left parent. So it's like for this one, the first vertex to the left of it that has a value less than it is z. So for x, I can say that if I know the values of y and z, if for some x I know the values of y and z, y is somewhere in here, z is some value in here, the number of intervals such that their minimum is x is like we have to multiply these options to set an ending point in here times the number of ways that we set an ending point in here. So it's gonna be like if these indices, for example, this is I of x, this is I of z, and this is I of y, the number of ways is gonna be I of y, I sub y minus I sub x times I sub x minus I sub z. So in these many intervals, we know that the minimum is x. So if we have this Cartesian tree, we know that for each vertex that in how many intervals this is the minimum element of that interval. So if we can only keep for every vertex what is its parent, that is easy, and what is the first vertex in the other direction. So it's like for each vertex it's like we can have two parents. The first parent in the right direction and in the first parent in the left direction. And one of them is the parent itself, and one of them is that direction of parent. So for example, in here, part of 1 and v is equal to u, part of 0 and v is equal to part of 0 and u. So we can easily, by having this Cartesian tree, we can have these parents for the vertices, and when we remove an element x from our tree, we can just simply merge those vertices in the subtree and update these values of parts and update the final answer that we're going to have. I mean, for these vertices, we can easily see that what is their answer, what is the number of intervals such that they are in the minimum of them. Okay, and this way the answer can be easily calculated. Is it clear? So this is gonna be all for this problem. We just have a Cartesian tree. Using this Cartesian tree, we can find out what is the minimum answer, and then I will take an example. And then we can each time update our Cartesian tree when we remove an element. If we want to talk about an example, let's consider this last permutation that they have here, this one. 8, 1, let me write it here first. We have 8, 1, 4, 6, 8, 1, 4, 6, 7, 3, 5, 2. So this is gonna be our permutation in that case. What we can say in here is that first we make our Cartesian tree. For example, 1 is the root, the left child is 8, the right child is 2, the right child is 2. Then for 2, the left child is 3. For 3, the right child is 5. The left child is 4 here. For 4, the right child is 6. Then for 6, the right child is 7. So this is going to be how our tree will look like in our Cartesian tree. Why the color doesn't seem good? Let me change the color. I think it's not very easy to see for you. Okay. So this is our tree. This is the tree that we have. This is our Cartesian tree. So what we can say is that for each of the elements, for example, like this 3, assume that for this 3, I want to find out that in how many, for this 3, I want to find out that in how many intervals 3 is the minimum one. Or let me consider a better example. As to consider this, let's say consider this 4 is not, none of them are good. So assume that we have 4. We have this 4. For this 4, I'm saying that I can have 2 parents for each vertex. One parent is the first ancestor that is in the right side of this vertex, and one of them is the first ancestor that is to the left side of this vertex. For example, for 4, the first ancestor that is to the right side of it is this 3. So for 4, the first vertex, the first parent in the right side is 3. And the first vertex in the left side is 1. The first ancestor in the left side of 4 is 1. And this can easily be calculated because it's like we have pair of 0 and 4 and pair of 1 and 4. Always one of the parents is your original parent. For example, pair of 1 and 4 here is going to be 3. And pair of 0 and 4 is going to be equal to pair of 0 and 3. Because whatever is the first ancestor of 3 to the left side is also the first ancestor of 4 in the left side. So anyway, we have these 2 parents. We know the first, it's like we know the first vertex to the right of 4 that is less than 4, and we have the first vertex to the left of 4 that is less than 4. And all the intervals that their left sides starts from somewhere in here, it starts in this step, in this space, and their ending point is in this space. All of them their minimum is 4. For all of them, their minimum is 4. So in here, it's like we have 3 choices. In here, we have 1 choice. So it's like 1 times 3 ways. For us to have an interval such that its minimum is x, its minimum value is x. So this is gonna so this way I can find for any value that in how many intervals this value is the minimum. And then when we have that, it's just enough to sum them up. For example, I know that 4 is minimum in 3 intervals, so I should multiply 3 by 4, and I sum this value up for all the x's, for all the values that I have. And if I do this, I have the final answer. And now the question is that what should we do when we remove a vertex? For example, assume that this 3 will be removed. The point is that when this 3 will be removed, we are going to have 2 chains that we need to merge these 2 chains. What are those 2 chains? For example, when we remove when we remove some x, we should merge the right chain of the left child and the left chain of the right child. The left chain of the right child. And how can we do that? Well, the point is that we can just do brute force. We do it very simply, in a very trivial way. We just do brute force. Each time we see that which one of them are smaller, we pick the one that is smaller. For example, assume that in here we have y, in here we have z, in here we have t, in here we have s, for example. And first, assume that y is less than z. Then first we put y as roots instead of x, and then the left child of v remain unchanged, and in the right child of v I will merge these two chains. And when I want to merge these two chains, I will compare z and t, and assume that z is smaller than t. So I put z in here, and the right child of z does not change, and in the left child of z I will merge these two chains again recursively. Now I compare s and t. Assume that s is smaller than t. So again I put s here, the right child of s will not change, and I put these two chains in here. Then for example I put t in here, the left child of t does not change, and then I recursively again merge the rest in here. And it will go on. And the point is that if the size of this one is, for example, s1, and the size of this one is s2, each time our pointers are going forward in one of these two. So the number of steps is s1 plus s2. So it's the sum of the sizes of these two. And the point is that each vertex will be considered only in one chain, because it's enough to find out what is the first place that they are not. I mean the direction of their parent changes. And that is going to be the only place that they're going to be considered in a chain. So in total, these mergings will take n steps. Will take, its order is going to be n. So that is going to be our final answer. This way our final answer can be calculated in O of n. Does this make sense? Please again use emojis or write in the chat if that is okay. Okay, awesome. So I think this one is okay as well. And about the last problem, I unfortunately haven't read that one. So I think maybe we cannot solve that today. Is there anyone who needs that problem to be solved? Oh, and the tag is not good. I don't want to spoil the problem for you, but the tag is not very good. It's a hard thing. If you want, I can spoil it for you. That's what is the tag was. So I think it's better. It's the best if we skip problem F. Example, please, for which problem? I mean, again, another example for problem E. Do you need more examples for problem E, or? So for problem E, the whole point, you know, I used an example, the last example in what we had. Let me also tell you on the example that I gave you myself, this random permutation that I generated. I'm saying, you know, in here, what we say is that assume that we have some additional nodes here as well. Let's add something. We have 10 in here, and for example, we also have 11 and 12 in here, for example. So we have also 11 and 12 in here. So when we remove vertex 2 from here, we are going to merge the left chain of this subtree, which is gonna be 6 and 7, and the right chain of this subtree, which is 5 and 10. And each time, how do we merge these two? Each time, first, we see that between 5 and 6, which one is smaller? We see that 5 is smaller. So we put 5 in here, and the left child of 5 will remain unchanged, comes in the left parts, and in the right child of 5, we will merge the rest of it, this chain and this chain. Again, in here we compare 6 and 10. Between 6 and 10, 6 is smaller. So I put 6 in here. And the right child of it will remain unchanged, which is empty. And in the left child, I will merge this chain and this chain. So we have 7 and 10 now. We put 7 in here, the right chain, child will remain the same, it remains 8. The left child, I will merge the remaining ones. In the remaining ones, only 10 is remained, so I just put 10 in here. So when I remove 2, these will be merged like this, and when I merge them, I can redefine the values of parents, the 2 parents that we had. I can calculate them again because I know that what is exactly the parent of each vertex, and I can calculate that what is exactly their parents, what is exactly their 2 parents, and I can update them, and this way I can update the answer, and I can know that for each I what is going to be the answer if I will be removed, because I can update my Cartesian tree, and when I update my Cartesian tree, from my Cartesian tree I can easily find out that what is that value of f of a permutation that I have. Does it make sense? Now, is it now clear? Then the intuition for A, as I didn't. The intuition for A, I explained A completely. If you want, you can check the video again. For A, I just said that each time the number of elements will be increased by k minus 1. So the size of your multiset will be increased by k minus 1. Okay. The size of a multiset will be increased by k minus 1. Initially the size is 1, at the end the size should become n. So the size should be increased by n minus 1, right? So we need at least sale of n minus 1 over k minus 1 steps for that. And if I want to show you my code for problem A, it's just enough to say that I see out n minus 1 over k minus 1, the sale of it. And this plus k minus 2 is in order to calculate the sale of this value. Is it clear now? Finding the range in Cartesian tree is O log n. Well, we do not need to find any range. We just need to find those 2 parents. And those can be calculated in O of 1. And when we have that, we know the range in which this element is going to be the minimum. Oh, I see. That's bad. Yeah, misreading the problem is really bad, is really harsh. Okay, do you have any other questions? Or comments or anything? Bring any full-fledged programming classes course. I want to, yeah, we are trying to do that. We are trying to do that. We are trying to make some free and accessible courses, and we are talking about that right now. We're working on that. Yeah, I really hope that I can make a free course to learn competitive programming for everyone. I have a list of DP problems. Some of them are DP on 3, most of them are DP on 3. If you want, I can send you the playlist. This is the playlist of 2000 plus DP problems. If you want, you can watch them. And they are the best problems that I could gather from different sources. It is from multiple years of teaching CP. And I tried to use the best problems that I know and have it as usable as I could. So I believe that it should be beneficial for you. So you can check that out and see. Yeah. Right now there are 6 videos, but I will try to add more problems. More problems like problem D. I don't have anything at top of my head. again, you can check that playlist. There are some DP on 3 problems there in that playlist. You can check that out. Maybe that helps. And also, if I found any problem related to that, similar to that, I will make a video for that and add that in that DP series. I will also tell you in the next live stream if I found anything. Right now, I don't have anything at the top of my head. Any other? Virtual is very helpful. Virtual contest is very helpful, I believe. I myself used to do a lot of virtuals when I was training competitive programming, but practicing is also what you have to do. I mean, for example, how many virtuals you're gonna have? You're gonna have, for example, 1 virtual or at most 2 virtuals per day. The rest of it, you're gonna need to solve those problems or solve other beautiful problems, etc. So virtual is very good, very helpful, but definitely it's not gonna be the only thing that you're gonna do. You're gonna solve problems as well. At least from those virtuals, you're gonna solve those problems that you didn't solve in the contest. You will solve them. I started CB 10 years ago. I mean, I saw my Codeforces accounts, and my registration is 10 years ago, as you can see in here. Right now, it's been 10. It went so fast. I can't believe it's been 10 years, but it is. It's weird. I was studying for IOI. When I started CP, I got a gold medal in Iran National OI, and I ended up at rank 6 in Iran at the end. And as you know, 4 people go to IOI. At that time, I ended up at rank 6 and didn't go to IOI, but later on I continued participating in CF contests, etc. And later on I became the coach of Iran in IOI. And now I'm ICBC World Finalist this year. Though I'm not in my best shape. It's been a long time that I didn't code a lot, but we hope that we can have good results in the ICBC. Do you have any other questions or comments? And guys, as I said, we're gonna have more live streams as well. I'm just trying to find an appropriate time. I will let you know in CF. We're gonna have more live streams, more useful live streams, and we're gonna discuss more things, especially out of topics stuff, and we're gonna talk with each other. My age right now is 24. The best source for learning number theory is the tag number theory in Codeforces. I mean, there's a tag for number theory, and you can solve the problems from that tag. And for DP, as I said, you have to solve a lot of problems. I also have another playlist. Maybe that is also gonna be useful for you. I also have another playlist that is DP problems with difficulty 1500s. So those problems can be helpful for those videos can be helpful for you as well. These are 1500s plus problems. The other one is 2000 plus problems. These all can be helpful for you. If you want, you can watch them. That really helps. You have to solve a lot of problems really for that. How do you make notes? I do not usually make notes, no. No, I usually do not make notes. Yeah. So, any other questions? I hope that you enjoyed this video, guys. And again, I would appreciate it if you like the video or subscribe to the channel or put a comment in the comment section of the video. That's gonna also be helpful. I think this way you can support my work, and I would definitely appreciate that if you do this. My competitive programming journey started 10 years ago. I joined Codeforces 10 years ago. Yeah, we will discuss that. I said about how to practice on CF before, especially again, let me send you the link of where I talked about it. I have almost talked about all these things before. The link of it, I had this video for starting. When you start, how to get out of newbie, what you shouldn't do and what you should do. It is for starting, and as you move on, you're gonna need to solve more and more problems. So you're gonna need to sort the problems in Codeforces by their difficulty and solve many more problems. So it depends on your stage. If you are just starting, you can watch those videos and see. I covered all these topics about how to start training on Codeforces, etc. And I will definitely try to make more guidelines as well. And we're gonna have also more live streams. As I said, I'm trying to add one more live streams per week, and right now I'm starting to talk with some people that you know about the project of making free courses for competitive programming. And we are really working on it, and I think soon you can hear about it if things go well. Problem D was a bit hard. I think its difficulty was not low. I think its difficulty was greater than specialist. It is possible that a specialist can solve it, but I think that average specialists won't. I mean, the difficulty of the problem should be more than that. Yeah. Yes, I can do that. If you want, I can do problem solving type streams for particular topics. Yeah, sure. Yeah, we can do that. I'll let you know. I think we should start faster these additional streams. I postpone it a lot, and maybe I should start more seriously starting those streams. That's so important that we do not postpone it more than it, and then we will do all those things. Thank you, guys. Thank you. Okay, so I think I'll see you very soon. Guys, what day works the best for you for live streams? For example, does Fridays work for you? For if you want to have additional live streams, maybe I can do it on Friday. On Fridays, we're gonna have an additional live stream and discuss other topics. Yes, I work at a startup right now. Other than CP, I work at a startup. I'll let you know more about it very soon. Okay, good. So we'll try to do it on Fridays. Good, awesome. How many questions per rating and how to know when to jump on next rating? It's always good that if your current rating is something, it's good if you solve problems. That's what I believe. It's good if you solve problems from the same rating. From the same rating that you have. For example, if your CF rating is 1500, it's good to solve problems with difficulty around 1500. That's what I believe that that's the most efficient way of training. Because if the problems you're solving are very hard, you can solve very little problems and you can learn very little, and you might stuck and you might even lose your motivation. There are many issues in solving problems that are harder for you, and also problems which are easier for you that they don't have much points for you. So I believe that the best difficulty is around the difficulty that you your current rating. That's the best difficulty that it can have. Yeah. Okay guys, so if Friday works for you, I think maybe we can start from this Friday. I will announce it very soon and we can do these live streams. That's gonna be good. That's gonna be great. Hi, how are you? Okay, so I think I'll see you next time. So goodbye for now. Thank you very much for joining today. It was really nice having you. Goodbye.